In this lesson, you will graph exponential functions and identify data that displays exponential behavior. So what is an exponential function? It's a function that can be expressed in the form y equals a to the power of x, and a has to be greater than 0, and it cannot be 1, because 1 to any power is just going to be 1. So we're talking about things that are greater than 1. So this is y equals 3 to the x. Let's graph it. So I used Desmos. And when I graph this on Desmos, I type in y equals 3, and then I hit a to the b, and that's the power of x. And as you can see this graph, it is in red, it is a curve. And this curve is always going to be approaching 0 as it is going to the left, and it's going to be approaching infinity as it's going up. This y-intercept, which we do need to know, is 1. You can see clearly where it's crossing the y-axis right here at 1. As far as a domain, what x values do you see? Well, I can go infinitely negative, and I could go infinitely positive. So we're going to say all real numbers. As far as a range, the values of y, if you'll look, it's never going to dip below 0. So my values of y are going to be 0 or anything above. So I'm going to say y when y is greater than or equal to 0. So this is an exponential function. It is a curve, and this function we're going to say is approaching 0 as it goes negative. So let's look at another example. Right here we have now a fraction to a power. This is 1/3 to the power of x. And what we want to do is look and see how the graph changes. So I typed in y equals 1/3. I hit a to the b for the power of x. And when we look at this curve, you're going to see some differences. Now the y-intercept is the same. So you see that y-intercept of 1 just like we did in the other graph. But this graph is approaching 0 as it increases positively. You're going to notice that I can have any x value just like last time. So my domain is all real numbers. And I'm going infinitely positive as it goes more negative. My range is actually going to be the same as last time as well, because as I am greater than 0, I'm never going to dip below that axis. So it's y when y is greater than or equal to 0. Now your difference with the other graph is that it is going to be increasing and it approaches 0 as it's getting greater. So a fractional base will be opening to the right as a curve, whereas a whole number base would be opening to the left. So in your book, it has exponential growth functions, and it has a model to show you how if there is a whole number base, it will be approaching to the left and opening to the left. An exponential decay function is going to be approaching to the right and opening to the right, and that is going to be a base between 0 and 1, a fractional base. So whole number is growth, fraction is decay. You try the example in your notes. Now we have a real-world problem where we have a function of soda. C is going to be the amount of soda consumed in billions of liters. T is going to be the time or years since 2000. I'm going to adjust this just a little bit and make it y equals 179 times 1.029 to the power of x. Now when I type it into my Desmos, I'll use the y and the x. I type this function in, and you will notice that you are going to have to zoom out because our numbers are so large. Our y-intercept is right here, and that's 179. So that tells me that when my time is 0, or in the year 2000, we have 179 billion liters that are consumed in soda. Now if I wanted to find years after 2000, that would be the x value. So if I want to find the year 2005, you're going to plug in and have 1.029 to the power of 5 and then multiply by 179. You find that now and then input it on your notes. The last thing that we're going to look at is exponential growth. So if you'll look at this table, we can see as we are decreasing here, we can see that this is divide by 2, divide by 2, divide by 2, divide by 2. That is what we call a common factor, and this is going to be exponential. This is exponential because I have this common division. over here, we're adding 6, adding 6, adding 6, adding 6. This is not exponential. We actually call this linear because it has a common difference. So just to review, a common factor is exponential, a common difference is linear. So let's try one more example, then you can try one in your notes. As this x is increasing, what is going on here? Well, 64 divide by 2, 32 divide by 2, 16 divide by 2. This is common division. So we would say that this is exponential, and the reason it says exponential because we have a common factor.